the final talk of today is Kihyun Kim, who will talk about rigidity of long-term dynamics for the self-dual Chern-Simons-Schrödinger equation within equivariance.
Thank you very much, and I'm sorry for the long title. And also I also want to thank the organizer for inviting me. So this talk will be based on my joint works with Sun-Sik in Korea. He was my PhD advisor and also Sungjin here. So here is a very simple 2D cubic nonlinear Schrödinger equation where everyone will know. But today I want to consider its engaged version. So in 90, the physicist P introduced the following engaged version of the 2D cubic nonlinear Schrödinger equation, which is called the Chern-Simons-Schrödinger. In that equation, the dynamics of the equation really depends on the value of G. So in this talk, I will actually focus on very special case where this constant is 1. So it is called critical, or it is also called the self-dual. And in that case, this equation was introduced by Jackie and P because they were able to find, in this very special case, they were able to find explicit static solutions. So which is called also vortices. So you can see in this display, this is very explicit. But even in the 2-dimensional cubic nonlinear Schrödinger equation there, still it is an open. We don't know any explicit formula of solitons. So for this covariant Chern-Simons-Schrödinger equation, the well-post is known in the following sense. So the equation is basically L2 critical, and it is also gauge invariant. So in the Coulomb gauge, so you need to first fix the gauge, and then in the Coulomb gauge, it is its local well-post is only proved in H1, and in the other gauge called heat gauge, there is a small H, almost optimal local well-postness, but still the L2 critical local well-postness is still open. And there are several works on the existence of solitary waves, and also for providing several sufficient conditions for finite time law for the global existence and scattering. So as I mentioned before, I will only consider the self-dual Chern-Simons-Schrödinger equation, and I will also impose the symmetry called equivariance symmetry. So self-dual and equivariance symmetry, which will be explained in the next slide. However, this equation, it is already very simplified, but this equation still have interesting nonlinear dynamics. And it turns out that it is at least I will believe that it turns out that it is a very nice mathematical model that we can rigorously demonstrate the Soliton resolution and also the classification of boundaries and also the rotation instability. But in this talk, I will only focus on these former 2 aspects. The rotational instability is some universal instability mechanism of some singularity formation for this equation, but I will not discuss in this talk. Okay, so here's the equation. So let us first fix some integer m. So this is called the equivariance index. Then the self-dual Chern-Simons-Schrödinger with an equivariance is an equation for a complex value scalar field. And the equation is given like this. So it is very similar to the nonlinear Schrödinger within symmetry, but we have additional the gauge potential terms like A theta and AT, whose formula is written like this. So let me emphasize that the equation depends on M, and in fact, the dynamics of the negative equivalent and positive equivalent index will be completely different. And also, as you can see in these formulas, the equation has no local nonlinearity, but the equation still has no derivative nonlinearity because of the symmetry reduction. So it is well-postness in L2 in the critical space L2. And also the equation is Hamiltonian. So here are also some basic facts. So we have conservation of energy and charge. So which is basically the gauge covariance generalization of the conserved quantities of 2D cubic analysis. So we have energy and also this. And it is also very similar to the mass critical analysis in the sense that we have L2 scaling and phase rotation symmetry like this. So I will call lambda as a scaling parameter and the gamma is a phase rotation parameter. And the equation also has a very special symmetry called the pseudo-conformal symmetry. So it basically reverses time like this, and also it scales the spatial variable in time-dependent way. And it can be also understood as a connection between the infinite time behavior and a finite time behavior of the nonlinear equation. And as already very well known in the 2D cubic analysis, we also have the virial identity. So let's go to the self-duality. One distinguished feature of this self-dual Chern-Simons-Schrödinger equation compared to the mass critical nonlinear Schrödinger is that the energy has this expression. So the energy is basically the L2 num square of some nonlinear operator act on the solution. So it is in particular, it is always non-negative. For the nonlinear Schrödinger equation, this kind of property only holds if the equation is linear or the equation is defocusing. But in those cases, as we know by the result of Dawson, there is only one possible global dynamics, which is just scattering. However, in this equation, we have a static solution. So this is not a scattering solution at all. And we have a static solution. And as I mentioned in the first slide, the JKMP found this kind of explicit formula for this static solution. And if we apply the L2 scaling and rotation symmetry, then we basically have a two-parameter family of solitons. So here's a brief comparison with the nonlinear Schrödinger equation. So this is the focusing case. So the energy might be negative. And in this equation, the solitary waves always have a non-trivial speed of phase rotation. So you should have this kind of mass term in the second order elliptic equation. And because of that, any solitary wave has an exponential spatial decay. And let me finally mention that this kind of property, the energy can be written like that, also exists without symmetry set. Okay. So let me turn to the dynamics. So as is very well known in the 2D cubic analysis, there are also very analogous results in this self-dual Chern-Simons-Schrödinger equation. So what is known is that it's the following. So if the solution has mass less than that of the solitary wave, then it has mass less. It has not enough mass to form a nonlinear dynamics. So the solution exists globally in time and also is scattered. So this is also very standard. And there's also a recent result by Li and Liu, who basically classified all the threshold behaviors. So unless solution is a global scattering solution, the solution must be either one of this, the global static solution Q, or a finite time block solution, which is obtained by applying the pseudo-conformal transform to this static solution. So this is a finite time block solution because if you see that if you assume that the time was initially negative and if you consider the time goes to 0, then you see that the spatial scale goes to 0 and also the L infinitum goes. So this is singular solution. So let me turn to the dynamics beyond the threshold. So we want to understand the dynamics of arbitrarily large data. So in these dispersive equations, there is a very famous conjecture called Soliton resolution conjecture, and there already has been a lot of progress, very remarkable progress. But the conjecture says that asymptotically in time, any solutions will decompose into the sum of modulated solitons and a radiation. So this Soliton resolution has been known for some restricted data setting, such as a sub-threshold where there are no solitons, or for defocusing cases. So defocusing case also can be included in this case. And also there are also several works on the slightly over threshold. So you can allow one soliton and a very small radiation. For arbitrary large data, by a completely different method, So several results. There are several results for some completely integral models. But for non-integral models, the very recent remarkable books says that the energy critical wave equation with a symmetry, they also satisfy the Soliton resolution. It is a rigorously proved within symmetry. However, also in this self-dual Chern-Simons-Schrödinger, we can also show the Soliton resolution, although we need to assume certain regularity and spatial decay assumptions. But we can prove the Soliton resolution as a consequence of the self-duality and also the non-locality of the problem. So in some sense, the non-locality of the problem will simplify the problem in this case. So here are some several notations. So this is the L2 scaling and phase rotation. Phase rotation symmetry applied to a function. And C will be the pseudo-conformal transform and Q static solution. And this is the explicit, the finite time block solution. And here are several notation for the weighted sublet space. So Soliton resolution, let me recall that the Soliton resolution is a statement for arbitrary solutions. So because we are considering arbitrary solution, let us divide into two cases. So finite time block solution and global solutions. So first, finite time block solutions. So let's assume that we are considering only the H1, the finite time block solutions having H1 regularity. Then in the case of negative equivariance index, so the result is that there is no such a finite time block solution. And in the non-negative case, we can see something in the asymptotic behavior. It is as follows. So there exists some scaling parameter and also phase rotation parameter and some radiation term, which in this setting we'll call an asymptotic profile, such that the solution must decompose into like this. In this statement, we don't know the behavior of lambda and gamma, but there exist certain these kind of parameters and also the profile, such that the solution must decompose like this. Moreover, we prove that the asymptotic profile has further regularity, and we can also prove an upper bound for the spatial scale. So the situation is something like if you are given any arbitrary solution, right, like this. So because it is just radial symmetry, so you have arbitrary solution, and then as time goes to finite time block time, then the solution must decompose into NA. Some of these two objects. So there is certain rigidity in the dynamics, asymptotic dynamics. And very similarly, let's consider the global in-time solutions. So in that case, we assume the weighted sublap regularity. And we can also say a similar thing for the negative equivariance case. So in the negative equivariance case, any such solution scatters. And in the non-negative equivariance case, there are two scenarios. So any forward in time global solutions, then either it scatters, or as in the previous slide, there exists a scaling and phase rotation parameter and a scattering profile, such that the solution basically decomposes into one soliton plus a scattering part. And a similar bound for the spatial parameter. Okay. So here will be some comments. So what was quite interesting in this decomposition is that there does not exist any multi-bubble trees in the I was something wrong in this here. But basically when the M is non-negative, we only saw the one soliton appearing in the resolution. So but this is very rigid compared to other situations, because in the case of nonlinear heat or nonlinear wave equations, there exist examples of multi-bubbles which exist globally in time, but it is still unknown whether a multi-bubble configuration exists in finite time, in the finite time block case. But in that sense, the fact that only one soliton appears in the resolution is very rigid, and we will in fact prove it as a consequence of defocusing nature in the exterior of soliton. We will come back to this. And for the best critical nonlinear Schrödinger case, a similar soliton resolution is already proved in the seminal series of papers by Miller and Raphael in this region. So this is basically slightly above the threshold. And in their work, they were also able to prove the following dichotomy for the behavior of the scaling parameter. So this is basically almost self-similar. So this is self-similar rate, and then you correct it by a log-log, which is a famous log-log rate, or the solution satisfies this kind of linear upper bound. However, in the self-pure Chern-Simons-Schrödinger, the dynamics is much more rigid in the sense that the log-log regime is excluded. However, this regime is still expected for if you consider more focusing Chern-Simons-Schrödinger equation. There is a formal argument in this paper. And also, in the radial case, we proved that the scaling parameter degenerates much faster than the linear rate. So this in particular says that there does not exist pseudo-conformal flow solution. And in fact, this is not a contradiction because ST solution, which is obtained by taking the pseudo-conform transform to the static solution, this does not belong to H1 because the soliton has a slow spatial decay. However, there are works with Sungjin and Sun-Sik Kwon that we can construct several examples of H1 finite time block solutions. So still, there exist many finite time block solutions in this radial case. So let's get into the proof. The key ingredient will be the following coercivity of energy, but I will say nonlinear coercivity because at some point there will be some non-perturbative argument in the proof of this nonlinear coercivity of energy. And to make it simpler, by pseudo-conformal transform, because it basically connects the behavior of infinite time behavior and the finite time behavior. By pseudo-conformal transform, it suffices to consider only this finite time block case. So in this case, we need to prove that in the negative equivariance case, there's no such a finite time block solution. And in the non-negative equivariance case, we need to prove the asymptotic decomposition and also some bounds for the scaling parameter. So on this slide is the proof for the negative equivariance case. So in the negative equivariance case, okay, we proceed by contradiction as always. And if we have a finite time block solution, then by the standard block criterion, the H.1 norm will diverge in finite time, but the energy is conserved, and also the L2 norm, and by mass conservation, it is also bounded. So we will have a contradiction if we can show this lower bound for the energy. So how to show this? We first apply the self-duality. So in this step, we first use the self-duality. So, and we expand using the definition of the Bogomolny operator. So this is something looks like a very, somehow at this moment, we want to use something like a Hardy inequality in the 2D with this operator. So in that sense, we will be able to prove this if there exists some constant satisfying this. So if the numerator is somehow strictly negative, but it's not too negative, then by following the proof of Hardy's inequality, then this implies this. And why this is true? First, we know that the M is negative, so this is already negative, and A theta is by definition it is always non-positive, so we already have this part. And also, on the other hand, by the definition of A theta, we can lower bound using a conserved quantity. So this is also lower bounded by this quantity. So this is the proof. Okay, so it was very simple. And then let me turn to the non-negative equivariance case. So as in the previous case, because the energy is conserved and the H.1 norm goes to infinity, so the solution will basically belong to a small energy regime. And then if we use some variation argument, in particular using a uniqueness of zero energy solution, let me recall at this moment that the energy was always non-negative. So the uniqueness of zero energy solutions will somehow give some qualitative statement for a very small energy solutions. So that's why we can have this kind of decomposition here. But at this moment, this decomposition does not give you the Soliton resolution, because this control, which is in some sense, I will interpret it as a local norm. This local norm is insufficient to give you the Soliton resolution. And there is a very standard way in the modulation analysis. Then we may fix the parameters using some certain orthogonality conditions. So to prove the Soliton resolution, well, here our main goal is again the nonlinear coercivity of energy. So what we will prove is the following estimate. So here, let me recall again that the static solution is a zero energy solution. So if you consider that this solution does not contribute to energy that much, then we want to prove this kind of coercivity estimate. And if we were able to prove this, then this in particular gives the H1 boundedness of the remainder part because of the scaling. So if you have the H1 boundedness, then this will be also H1 bounded. And following the argument in the paper on mirror file, then this implies that the remainder part is L2 Cauchy. And this is also a very standard modulation aspect. So everything is reduced to the proof of this nonlinear coercivity of energy. How do you show this? Here, let me remark that because the L2 norm is not small, so this is a non-perturbative estimate, as in the negative equivariance case. This is non-perturbative. And to prove this, as before, we use the self-duality and expand the energy like this. So in the interior region, because we already have that the epsilon part has a small local norm, so this interior region is perturbative. So we can span our orthogonality conditions to show that the interior is basically, roughly speaking, it satisfies this kind of linear coercivity. However, in the exterior region, now we use the non-locality in the sense that the gauge potential term, Q, this goes to strictly negative value, so that it changes the numerator, this term, to this term. Now you see that as in the proof for the negative equivariance case, we can proceed in the negative equivariance case, and the integral will be lower bounded by the H.1 norm of the epsilon squared. So this is the whole proof. So now let me turn to the classification problem. So by Soliton resolution, we saw that any finite time block solutions having H1 regularity decomposed like this, and also we prove this kind of upper bound. So the very natural problem might be to classify all possible behavior of lambda, the scaling parameter, and this phase rotation parameter. And it turns out that there is a very big difference between the radial case and the high equivariance. I will call this case high equivariance. So there will be a very huge difference. So I will first discuss this high equivariance case, which is easier. So in the high equivariance case, this linear upper bound for the spatial for the scaling parameter this is saturated by the pseudo-conformal block solution, which is obtained by taking the the pseudo-conformal transform to the static solution. Then we ask that, is there any finite time Bloom regime other than the pseudo-conformal? And before that, in my previous works, we were able to construct several examples of finite time block solutions. Of course, different from ST solution, but they are all somehow the pseudo-conformal block solution. They all have the linear behavior of the scaling parameter. And the answer now turns out to be, so the answer now turns out to be false in the sense that in this high equivariance case, and if you assume a smooth regularity, a very smooth regularity, then any finite time block solution must be a pseudo-conformal solution. So in this decomposition, we can basically take the scaling parameter as a linear function, and we can freeze the rotation parameter like this. And as a byproduct of our analysis, we can also say that there are certain universal structure in the asymptotic profile. So in particular, when M is 1 or 2, then the asymptotic profile must have some non-trivial structure near the origin. And let me mention here that the this kind of classification problem. So there have been quite a lot of the block constructions recently, but the classification problem is in some sense a reverse question. But the difficulty, the usual difficulty for this kind of classification problem is that we need to deal with all arbitrary finite time block solutions. And the only assumption that I impose is, like this kind of regularity. So we don't have much assumptions. So I'll say that that's the difficulty, because usually in the block constructions you can put as many as you want the bootstrap hypothesis when you construct block solutions, as long as you can also propagate them. But this is somehow the reverse question, and the difficulty is that we don't have many hypotheses, a priori hypothesis that we can really use. And a corollary will be the following. So a corollary is the refined Soliton resolution for very smooth, very spatially localized solutions in the high equivalent case. So one of the following must hold. So if you're given any solution, any smooth and spatially localized solution, one of the following holds. So the solution is a pseudo-conformal solution, or the U is a global scattering solution, or the solution scatters to some fixed soliton plus a radiation. So these are the all possible behaviors for this Chern-Simons-Schrödinger equation in the high equivariance case. And this is in some sense, and I was also very much inspired from the works by Martin, Miller, and Raphael, who considered the near soliton dynamics for the L2 critical KdV equation. The result is the following. The assumption is the following. So the initial data is initially close to the to the solitary wave. It is not a static solution, but it's close to a solitary wave profile. And the initial data has a strong spatial decay on the right. Then the result is the following. So one of the following scenarios holds. Maybe you can compare this with this. A solution blows up in finite time with this linear rate, or the solution exits the soliton tube, and it is conjectured that this solution is a global scattering solution. Or the solution scatters to a modulated soliton with some fixed scale and velocity. So in our case, we were able to do an arbitrary large solution thanks to many good properties from the Chern-Simons-Schrödinger equation. But somehow I needed to assume a more regularity in the setting. And as many people here will know, the smoothing properties of the KdV type equation and the nonlinear Schrödinger type equations are quite different. And here, let me also mention, more broadly speaking, the classification problem of type 2 blob solutions. By definition, type 2 is a non-self cylinder. And here I want to assume like the radial symmetry or something like that, because without any symmetry assumptions, type 2 will be very, very wild. So here I want to assume the radial symmetry here. So, or equivariant symmetry, obviously. So in that case, even in that case, this kind of classification problem is mostly open. As far as I know, for the nonlinear heat equation on the radial symmetry, there are several results on the non-existence of type 2, depending on the range of the exponent. And there is also very interesting one by Mizoguchi. She classified the behavior of the L infinity rooms if you purely assume that the solution is finite time blob solution, and also assume that it is type 2. And also her argument really uses the maximum principle quite a lot. So she needed to assume a non-negative initial data assumption. So the approach is completely different from what we usually do in hyperbolic or dispersive case. And she also recently proved a similar result for the 2D Keller-Ziegler model for radial and again the non-negative initial data. But in that model, this assumption is very natural. And for the dispersive case, what I only know as a complete description of the dynamics is the Martin-Merrill file for critical KDB, but they still needed to assume the near Soliton, initially near Soliton. For the best critical NLS case, let me come back to this. So in this case, the Raphael proof, assuming that this slightly beyond the threshold, if a solution is a blob, finite time blob solution, and we already saw this kind of dichotomy, and it is a very long-standing open question since from this paper, maybe 20 years right now. So whether exotic regime exists or not, this is still a long-standing open problem. Okay, so let me go to the radial case. For those who are familiar with the equivalent wave maps or the Schrödinger maps or harmonic map heap flows, the radial case is somewhat similar to the one equivalent wave maps or Schrödinger maps and the equation as you like. But the radial case is similar to the one equivalence, and the high equivalence is somehow similar to the much more higher equations. So in the radial case, a completely different picture is expected. For rough solutions, there's no rigidity. And in fact, we were able to, we still need to finish the paper, but there exists, we were able to construct finite time blob solutions such that the scaling parameter behaves like this. And in this rate, we can allow any real number greater than 1. However, for smooth solutions, we constructed a smooth finite time blob solution. And in fact, the initial data can be chosen as a compactly supported. For these kind of solutions, we are able to construct this range. And the conjecture is the following. So the conjecture is that taking the analogy between the one equivalent geometric equation and the radial CSS, the conjecture is that there will be a Carnot family of possible balloon rates of the. Of course, the construction should be done, but I think that it is possible, but maybe technical difficulties, but I think it's possible. And the real difficulty will be to prove that any smooth finite time blob solutions will have blow up with this rate. Okay, so in the remaining time, let me go through strategy of the proof. So we're basically considering the high equivalent case. And we already know that by Soliton resolution, we already have this kind of decomposition. And our goal was to show that we can in fact choose the scaling and phase rotation parameter like this. So in some sense, we need to know more refined dynamics of the scaling and phase rotation parameter. So the key ingredients are the following. in the analysis for any solutions to CSS, regardless it is a block solution or not, we will be able to identify the singular and regular parts of the solution such that the singular part, singular with respect to the H3 topology, the singular part, the dynamics of the singular part will be governed by a universal modulation dynamics, and the regular parts remains H3 bound. So what this means is that even if this is U is a finite block solution, then of course the H3 known will blow up, of course, because of the block criterion. But the singular structure is somehow universal, and if you subtract the singular part, then we will have a H3 bounded remaining part. So in some sense, the previous Soliton resolution result gives a H1 decomposition. Of course, in that case, you also need to show that the singular part has a profile which is the Soliton. But of course, but the Soliton resolution basically said in our proof, it basically said that the singular part is given by the modulated Soliton, and the remaining part, which looks like this, is H1 bound. So to understand the refined dynamics of the modulation parameter, we need to understand the linearized dynamics. The linearized dynamics is as follows. So as in the proof of the Soliton resolution, we know that the solution can be decomposed as a modulated Soliton plus a remainder term, where the remainder term in the Soliton scale, it is small. However, the remainder term does not have a small L2, but it is locally small in the Soliton scale. But anyway, that will disappear, and that will suffice. So here is a very standard procedure. So we linearize, and I will denote this the minus imaginary number times the calligraphic L2 as a linearized operator. And we want to understand the invariance of space decomposition for this linearized role. So this is only rigorous for large M, where the Soliton decays as the spatial decay of Soliton is very nice. But the rough picture is that we can decompose this flow into invariant spaces, having the dimension 4. The generalized corner, has a dimension 4, and also with this codimension 4 space, which is also invariant under 4. Then we need to understand the dynamics in these spaces as usual. So in the dynamics in the 4-dimensional space, the generalized corner space, it has a Jordan form like that. So this is in fact quite simpler compared to the NLS case. So I believe that this makes this Chern-Simons-Schrödinger equation much more simpler, and it has a rigid dynamics compared to the NLS case. And on this codimension 4 space, there will be some monotonicity in this codimension 4 space, in infinite dimensional space. So for the nonlinear solution, as usual, we want to decompose it using the modulation analysis. We want to decompose somehow like this, where the 4-dimensional space, the generalized corner part, will correspond to this profile part with additional parameters b and eta, and also the scaling and phase rotation parameter. This will be the 4-dimensional part of the solution, nonlinear solution. And epsilon will be just considered as the part of the solution which belongs to the codimension 4 part, where there will be certain monotonicities. And of course, we need to construct the modified profile, and also we need to drive formal dynamics. And also we need to propagate smallness or boundedness by showing certain monotonous estimates. So here's the slide for the formal modulation dynamics. But I want to skip it. But maybe you can see my paper, or basically I just use the method of telecomputation, which is very well explained in the paper of Rafael Raniewski in the case of equivariant wavelengths. So there's nothing too special about this. But the conclusion is that we'll have a formal modulation equations like this, where S is a renormalized time variable, which is defined like this. And this will be the formal modulation equations. So you have you have a system of four differential equations. And this can be integrated because you have two conserved quantities, this one and this one. So the important fact is that the blow up will only happen if eta is completely zero and vanishes, because this is the conserved quantity. If eta is non-zero, then of course this denominator cannot go to zero. And if eta is zero, and also if this conserved quantity L square is non-zero, and then if you integrate this modulation equation, then you will see kind of pseudo-conformity. So in this slide, I want to explain how the H3 decomposition implies the rigidity in the real problem. So as I mentioned in the very first slide for the strategy, I mentioned that I can decompose the nonlinear solution into the singular part and a regular part. And the regular part remains H3 bounded. And here I want to convince you that the H3 boundedness will suffice to justify the modulation equations. So this is a little bit technical estimate, but it is also quite standard in the modulation analysis. So if epsilon belongs to this specific plane as this specific space, an invariant subspace, and this is also not true when the M is very small, but let's just assume it. If epsilon belongs to this space, then it is natural to expect there exists certain local ones, so that this is also standard estimate. But anyway, the conclusion is that we will have this kind of differential inequality. With this differential inequality, if we can prove that this part, which is in this coefficient, if this part is integral in time, and then by Gronow's inequality, this term must converge to a non-zero. And in the block case, we know that in the block case, by the hypothesis, we have lambda goes to zero. This is the block scenario. So this is that this term goes to the beta over lambda, which is basically the square root of the b squared plus eta squared divided by lambda. This goes to a non-zero value. Then it is not difficult to compute the rigidity. And let's see how the H3 boundedness imply in this part. And this is very easy, because if epsilon is bounded if the remainder part is bounded in high sublevel, then the local norm will be somehow bounded by the Hardy norm, by Hardy's inequality. And by scaling, we will have some scaling factors here. So if k is greater than or equal to 2, then this is bounded by. So everything is now reduced to prove somehow the HK boundedness, but in this talk it will be I will show this with k equals 3. To prove this, we actually also use we use the method, the energy method with reversibility to prove the H3 boundedness. So again, this is not new. So this is the strategy that somehow you need in the global analysis. There will always appear if you just do the energy method. It always appears the non-perturbative terms, and the idea is that to use certain monotonicity estimates to treat that non-perturbative terms. And this idea was first introduced in the work of Roniansky and Strevens for the high equivariant the wave maps, and it's developed in many of these works. But the difficulty is that But the difficulty is that we are not in the situation of constructing blob solutions. So we need to do arbitrary solutions. So we cannot assume any dynamical controls, such as like this. This is basically says that the solution is shrinking. Or this is a little bit technical, but this says that the instability is somehow turned on. However, from the proof of Soliton resolution, we actually have a certain size control by the nonlinear coercive energy, which is, and my main claim is that this size control, not the dynamical controls, the size control is enough for the proof of H3 boundaries. So now I want to explain the monotonicity statement in the dynamics of the codimension force space. So this was the linear race problem. And it is also standard in this kind of the self-dual equations is that the linearized operator admits this kind of factorization. This just follows from the Hamiltonian structure and the self-duality. And what was used in the work of Rodniansky disturbance is that one can consider a supersymmetry conjugate like that. And a very important observation here is that observed in this paper is that and this conjugated linear operator is in fact the same as the one usually arising in the analysis of K equivalent wavelengths with n+1 wavelengths or Schrödinger maps. And then using the experience using our experience in those previous works on the wave or Schrödinger maps, we can take, it is natural to take a further conjugation by this new operator. Then basically we will arrive, after taking two first order differential operators, we arrive at this equation for the epsilon2. The epsilon2 is defined by taking these two somehow natural linear operators. And then the linearized Hamiltonian has a repulsive property. So that if you do the virial type computation, then you will see some space-time lower bound. But in the actual proof, the virial is not very practical because this term is not bounded, because we didn't assume any, the weighted Sobolev type bounds for the solution. We only assume just an unweighted Sobolev. So the virial is not very effective, but there is a very effective Morris type monotonicity. One can construct such a Morris functional. So then we still using also we use the high equivalent assumption to have certain good monotonicities. This will be quite subtle in the radial case because I really use this one in the radial case. And this operator, it looks very much like a 2D Laplace. So the Morris estimate will be solved. Then we construct an energy Morris functional just like this. And then what this function satisfies, it first satisfies a coercivity estimate. So it is coercive, so that if you control this functional, then you can also control many associated the Sobolev norms of epsilon. And it also has a very nice propagation property, like this. Then if you have this kind of property, then by Gromov, you will have it. And the claim is that the size control is enough to have it. The remaining slides are a little bit technical, so let me skip it. And thank you very much.